So our next speaker is Professor Jeff Kahn, telling us something about the cover time.
Yeah, okay. Yeah, the technical issue is that the speaker is technologically incompetent. Yeah, okay, so let me start. Everything I say is joint with Quentin Dubroff. I should say the slides are for a longer, slightly longer talk, so you may see me skipping. I don't mind if you ask questions. Do not ever put anything in the chat. I will not see. All right. So let's see. We're talking about simple graphs, connected, finite, but simple is important. We're on V. V has n vertices. We're talking about ordinary random walk, which just means you start somewhere. I'm not going to worry about where you start. And then wherever you are, you look around and choose uniformly from your neighbors and move. So this is a Markov chain. You know where you are, but you don't remember how you got there. Right? Let me remind you, the cover time it's a random variable. It's how long it takes you to see every vertex. All right. So let me give you an example. Suppose that the graph is the complete graph. Right, then this is basically just the coupon collector problem. It means you have n coupons. Every day you get a uniform coupon. And the question is, how long does it take you to see them all? All right, now it's not literally coupon collector, because if you're sitting on V, you have to move to some other vertex. So if I put loops, then actually this would be more or less exactly the coupon collector problem. All right, at any rate, that's a basic classic probabilistic construct. The answer is it takes about n log n steps. On average, it takes about n log n steps to see all the vertices. Log is log based, log is natural log. Famous result of Uri Feiga from 95 says that you get more or less I'm still traumatized from the technology. If you give me any n vertex graph, then the cover time could be much bigger, but it's never much less than what it would be for the complete graph, right? So you would think that, I use fastest to mean that the cover time is a minimum. It's not, for stupid reasons, it's not quite true that the complete graph is fastest. But this is a separate issue. I don't want to talk about it now. But more or less, on any n vertex graph, the cover time is about n log n. Right now, so I recommend Feiga's paper. It's a short paper. It's something people struggled with, and eventually it was not so hard, but it's very pretty. We want to do something different. I'm not going to give you n log n steps. All I'm going to give you is constant n. So C is 1,000. All right. So I let you take Cn steps. And the question is, how likely are you to see all the vertices in that limited time? For example, let me try to find a place to write. So I'll write over in the right-hand margin here. For instance, if I look at Kn, then the probability, this is the probability that I see everything in time Cn is right around here, e to the minus epsilon n, where epsilon is e to the minus c. All right, so the probability that you see all the vertices in this short time is exponentially small. It's e to the minus epsilon n. Epsilon's a small function of c, but it's a constant, right? And the conjecture we want to talk about was suggested by Itai Benjamini in 2009. And it says you get the same thing on any n vertex graph. Right. So formally we would say this, you get a C, I give you a C, right? Then there is an epsilon which depends on C, but on nothing else, so that for any n, at any n vertex graph, the probability that your walk covers the whole graph in time C times n is less than e to the minus epsilon. Okay, so that's what we want to talk about. I was in love with this problem from the moment I saw it in 2010. This is what I like. It's kind of, you couldn't name a more basic question. It's as simple as it could get. It looks like, yeah, you're going to do this in 5 minutes. And it turns out that it's really hard to get any handle on. All right, so the history is what you see in the next 3 or 4 lines. I don't know if that's because people forgot about the problem or because nobody got anywhere. At any rate, it starts with this. This is another beautiful, highly recommended paper, a kind of miraculous paper. Benjamini, Ori Gorel Gorevich, and that's Ben Morris, not Rob Morris. And they prove that Benjamini's conjecture is true if you bound the degree. All right. So for any particular degree bound D, you get this exponential decay. The only difference is that now the epsilon is also going to have to depend on D. And the dependence is not very good, but all right. In 2012, Amir Yehudayov proved it for trees. You might think that's going to be easy. It's not. This is another pretty result. And he also proved, well, all right, he pointed out that it's true for expanders. The point here, expander, excuse me, expander refers to second eigenvalue. We don't have to be too careful. What he really does is he points out that there's this older result of David Gilman, which is something to do with tail bounds for expanders. That's not an easy result. But once you have that result, Benjamini's conjecture follows pretty easily. Okay, so that's the history. If you looked at the abstract, you know what we're talking about. The conjecture is true. Ideally, I would now send you home for a week and let you think about this to convince yourself that it's really not so easy to see what to do with this problem because it looks easy. All right, but this is a 40-minute talk, so we won't do that. What I will do, I'll spend a few minutes sort of just playing with the problem. This won't have too much to do with what I'm going to tell you, but I want to get used to the problem because I suspect many of you have never thought about such things. So let me say 2 things, or raise 2 issues. First of all, pretty much anyone who would think about such a problem would have the first reaction that this is going to be martingale concentration. Where am I going to get an exponential tail bound? I'll get it from some kind of martingale concentration. And let me say this, for those of you who've never seen anything like this, the story would be something like this. I'm going to define a function, excuse me. I'm going to define some function y. I get to choose the function, right? So it's a function of the walk. And I'm going to let yi be the expected value of y, given what I've seen through the first I steps of the walk. And then I want this, that's a martingale, that's called a Dubroff martingale. Never mind what it means. The interesting condition is the thing with the red arrow. This is, I want the bounded differences condition, right? Which says that taking one step of the walk never changes the expectation by very much. Okay, so nothing you do in one step could change the expected value of y by, say, 1,000, all right? If that's true, then you get this kind of natural upper bound on large deviations. So it says that the probability that you are away from the mean by at least t is less than e to the minus something like t squared over m. All right, where m is, remember, m is the number of steps. Okay, so if t was linear in n, if t was some constant multiple of n, and we're going to assume that the number of steps m is linear in n, then this is an exponential bound, right? And t squared over m is linear. Okay, so I don't expect I'm fooling anybody. I'm not trying to fool anybody. The bounded difference condition is nonsense, right? Or often nonsense. So let me take the kind of most naive y that one could think of namely the number of missed vertices. All right. So let us suppose that we can at least convince ourselves that the expected number of missed vertices is constant depth. Okay. If that's true, then covering everything means that I differ from the mean by that constant n. I want to say the number of missed vertices is 0. So if I go up to the line up here where I'm drawing the dot, all right, t is now linear, m is linear, so I get my exponential tailback. Right. The only thing is, as I said, the bounded differences condition is simply nonsense, and I don't need to give it to you concretely. It's obvious but this shows you some difficulty with random walk. I'm at a vertex, all right, and I don't know what my graph. I have no idea what this graph looks like. Well, maybe I move east from this vertex and I'm in one part of the graph where I get one kind of behavior. Maybe I move west, then I'm in a different part. I get an entirely different behavior. And so it just says you can't, in general, it doesn't say you cannot use martingale concentration, but it says you got to be careful, right? Most of the time, this condition will not hold. All right, so that's one difficulty, and we will use martingale concentration somewhere. The other is this: if I did have the time to send you home to think about this problem, I believe you would quickly run into this issue, which I'll call the problem of reentries. Right. So picture a graph like the one I've drawn. You've got a bunch of clusters of some kind, loosely linked. And think about the walk kind of wandering around in a cluster for a while and then moving on to another cluster and working on that and eventually coming back, right? And the question is, how do I know that it doesn't keep coming back to the place that's going to be most helpful to cover? So why, maybe it covered 90% of this first cluster. I'm trying to find the color that will show up. All right, so I'm all right. And after coloring 90% of the cluster, it goes away, it comes back, and it always comes back to the part it hasn't seen yet. Now, that's not likely, but it turns out it's really hard to control, really hard to say it doesn't happen. This Benjamini et al. Paper that I am saying is so nice actually deals with this by not dealing with it, by allowing, they just say, once I get out of this cluster, I'm going to allow some adversary, some demon, to pick up the token that's moving around and put it back in the worst possible place, and they will still deal with that. Right. Again, a beautiful paper. Yehudayov proved it for trees. For trees, reentries are not really an issue because, if you go away from a vertex, where you're coming back. And the other thing I would say, and then I'm going to continue, is in what we do, this is mysterious, the problem of reentries just disappears. We never have to deal with it, and I don't actually understand why that's true, but it evaporates. Okay, so again, you're free to ask questions. I'm sure that this is unfamiliar territory for a lot of you. Also for me. Here's the plan, right? I'm going to tell you with theorem A. Theorem A is actually the Markov chain theorem that was also in the abstract. And that's where things start. And it's kind of step one of the proof of our main theorem. Theorem 1 will look like theorem A. Okay, so I'll tell you theorem A. It's what you can be reading it. It's on the slide here. Then I'll just pretty much just outline the proof of theorem 1. And then if we have time, and you can prevent that by asking questions, if we have time, then I'll try to give you an indication of how you prove theorem A. Okay, so theorem A, we're talking about Markov chains. I'm going to have to assume you know what a Markov chain is. Again, the state space is going to be V, the number of vertices, the number of states is going to be N. And the odd thing here is that for some historical reason, transition probabilities are denoted phi. All right, here's theorem A. It says, again, I'm interested in covering with Cn steps. So you give me a C, then there's going to be a delta that depends only on C. So that if I promise you that all the transition probabilities are small, meaning smaller than delta, then you get the thing with the red arrow here, that's Benjamini's conclusion. Okay, so you get that conclusion for Markov chains in which the transition probabilities are small enough relative to the given C. All right. Let me, maybe this is a minor point, but let me emphasize a little bit. We're in Markov chains now, so you can loop, right? A vertex can move to it. You can go from a state right back to the same state. When I talk about transition probabilities, I am not talking about that. So it's always moving from one state to another state. Okay. So that's theorem A. What does it say for graphs? Well, in a graph, the transition probability is just 1 over degree, right? You're moving to a uniformly chosen neighbor. So the small transition probability condition is just degrees are large. So for graphs, what this tells us is that Benjamini's conjecture is true if my graph has all degrees bigger than some lower bound D, which again has to be a function of C. All right. And for instance, that proves Benjamini's conjecture for the Hamming cube. And this is something, you know, being good combinatorialists, this is one of the first things we tried, and we couldn't do it. But in the Hamming cube, the degrees are big, right? They're functions of n, they're tending to infinity. So that's all right. It's not an expander, so it's not covered by Yehudayov. And we don't know a simple, theorem A is nice. It's not the hardest thing in the world, but it's not easy. And that's the only way we know to do this. And it would be nice to see a different way. Let me quickly say this BGM proved Benjamini's conjecture under any upper bound on degrees. We prove it for some lower bound on degrees. So can you combine them? It doesn't look good. You're welcome. I'd be delighted to be proved wrong, but it seems this is not a promising direction. All right, and in fact, nothing I've told you so far has much to do with what we wind up doing to prove this. Okay, so that's theorem A. And the plan was now to sketch theorem 1. Again, feel free to ask questions. If you see these brackets, this is my personal code. It means this is, if we had a blackboard, this is the thing on the blackboard that I would be pointing to. So this is just reminding you what theorem 1 was. And I'm trying to give you an idea of how it goes. Let me just, for the purposes of this talk, I'm gonna write gamma.
Question, Jeff.
Yes.
Is it easier for regular graphs?
No.
No.
Well, Hamming cube is regular, right?
Right, yeah, but for regular, at least knowing it for big degrees and for small degrees, you know it for all. But that's it.
Yeah, that's true. But we have to prove it. That's true. This is certainly true.
Okay.
Yeah, all right.
Okay.
That's a fair point. But okay, good. Let's see. So again, gamma is first. I'm having problems with my fancy Apple Pencil, but there it is. Gamma is 0.1. Okay, so it's not really a parameter. And step 1, I said it's going to be a generalization of theorem A. So theorem 2 will generalize theorem A. We're still doing Markov chains, so the stuff The stuff over here, I've already told you. So theorem 2 says this: you give me a C, then again, there's going to be some delta, which is going to depend on C. So that if all the transition probabilities are less than delta, then I get Benjamini's conclusion, except that now I'm only interested in transition probabilities. The important thing to read in this highlighted line is this. So I'm only going to be interested in transition probabilities where I don't care what V is, but W has to be in the specified set W. And the assumption is that W is pretty big, right? So W is at least a tenth of the vertices. Okay, so if you have a tenth of the vertices, so that all transition probabilities into those vertices are small, then you're exponentially unlikely to cover in this linear time. In fact, as you would guess from the statement, you're exponentially unlikely to cover even the vertices in W. Okay, that's theorem 2. It will still be at the top, I think. Yeah, there it is again. Okay. Step 2 is a corollary. I call it partitions. You see a partition in the lower right in this beautiful work of art in the lower right-hand part of the screen. So it's a partition because the blank part is the last piece of the partition. All right, so step 2 is a corollary of theorem 2. As sometimes happens, it takes much longer to say the corollary than to prove it. The proof is down in the last 2 lines. I hope you can see this down in the last 2 lines of the slide. Okay, so the corollary will eventually, it will say, I'm highlighting, or I'm pretending, again, the pencil doesn't work. There we go. I'm highlighting that eventually we're getting Benjamini's conclusion. All right, and so the corollary will say we get it under a bunch of assumptions, assuming we have this whole setup, which I try to describe. Okay, so the setup is this. You're going to have V1 up to Vk. These will be disjoint subsets of the state space. We're still doing Markov chains. I promise you that their union is big. So the union contains a tenth of the vertices. And I promise you that the VIs themselves are fairly big, meaning they're bigger than theta n, where theta is up at the top is some other constant. And theta will be a function of C, and it will be pretty small, but it will still be a constant, right? So the VIs have some small linear cells. All right. And I think, let me now skip 2 lines and jump to where I'm highlighting. Was that a question or a dog? Or okay. I have to talk about the induced chain. So if I'm looking at a Markov chain and I give you some set of states W, then the induced chain on W, or the chain also called the chain watched on W, it just means I'm running the full chain. I haven't actually done anything to the chain, but I only watch when it's in W. So I'm reading the newspaper and I have a little alarm clock that goes off whenever the thing goes into a vertex of W, a point of W. The thing rings, I wake up, I write down where it is, I go back to sleep, and it rings again the next time it's in W. And that's a Markov chain on W, and it's called the induced chain. Okay, so we have these VIs, and we will be interested in the induced chains on those VIs. So I'm running, you're looking at this picture, I'm running the chain on the entire picture, but for each particular eye, I can also look at what that chain is doing just at the times when it's in VI. Okay, given that, I'm going to try to apply theorem 2 to the VIs. And so what I will have is in each VI, I will have a set UI. All right, maybe it should have been WI, but it's UI. And it's a pretty big piece of VI. Just as in theorem 2, it's at least a tenth of the vertices of VI, right? And I have the theorem 2 hypothesis, namely when I look at the induced chain on VI, all the transition probabilities into UI are small, right? So I'm just describing, all I'm doing is I'm describing the assumptions of theorem 2 in this context. And then the conclusion is that you get Benjamini's conjecture, that the probability that you cover, even the probability that you cover all the VIs in time Cn is small, okay? Now notice, maybe something that's worth commenting on here is when I write down the small transition probability hypothesis, I'm over on the right-hand side highlighting this delta. That delta is a function of C. You could say n gamma, but gamma is fixed. It's kind of silly. All right, so this upper bound is a function of C. It is not a function of theta. All right, it's not a function of this other constant theta. The truth is it could be. The corollary would still be true, but the corollary would no longer be good for anything. That's kind of a long story, so let me not try to get into it. Okay, at any rate, this is the corollary. If you have that setup that I've just been describing, then in fact you have this exponential tail bound. The epsilon in the tail bound does depend on theta. It very much depends on theta, but theta is a function of C, so this is still all right. So this is really e to the minus something depending on C times n. Let's see how I'm doing here on time. I started 5 minutes late, I think. Is that okay? So,
sure.
okay. And Noga asked a question that took at least 10 minutes. So,
right. Yes.
All right.
We have about 15 minutes.
Yeah. Okay. Let's see. But now I have 5 minutes to remember what I was talking about. Oh yeah. The proof of the corollary. So, and I won't prove it. It's really these two lines. I'm walking for Cn steps. So how much time am I spending in the VIs? Well, not more than C times n. And C times n is the CIs, the VIs, excuse me. The VIs cover a tenth of the vertices. So C times n is at most 10C times the number of vertices in the VIs. Okay, so I'm spending time at most 10 times C times the number of vertices, which means that's also true for some particular VI. There is a VI where the time I spend in VI is at most 10 times C times the number of vertices in VI. But now I can apply theorem 2 in that particular VI. What's the probability that I take a walk, which is the induced walk in this case, in that particular VI, and I cover everything in time 10C times the size of VI, where I promise you that in VI I have this transition probability bound. Right? So theorem 2 says that's extremely unlikely. It's exponentially unlikely, where now the exponential is in the size of VI, but that is still linear. Right? It's still at least theta times n. So the probability of doing this in any particular VI is exponentially small. You can add up, the so-called union bound, you can add the probabilities over the VIs, but there are only a bounded number of VIs. So this is really not a point of interest. And that's it. That's the proof of the corollary. Okay. Well, that's step 2. So fine. So, and this is, I should say, historically, this is where the whole thing fell, just ground to a halt, because, and really looked hopeless for a long time, because why do you expect to see such a partition? Do you expect to see such a partition in any n vertex graph? And we didn't really think so when we were stuck on it for a long time. And the answer is, the truth is, we're still stuck on it. We don't know. But we know enough. So it turns out that there are a couple kind of exceptional situations, which I'm going to call X. If neither of these exceptional situations occurs, then there actually is a partition. If either of them does occur, then we can deal with it in some other way. And I'm not going to tell you what X is. One thing I will say is that X hides an interesting point. Namely, in everything I am telling you or not telling you, the only place where I need the graph to be simple. Remember I said at the beginning the graph is simple. Quick exercise that you can do on the side. If I don't say simple, Benjamini's conjecture is nonsense. So I do have to say simple, but that shows up only in one of these funny situations that I'm just alluding to, I'm not talking about. Okay, at any rate, so most of the time there is a partition. And this is, getting the partition is a long story. I would say, by the way, there's nothing in this paper that there are no excruciating details. There's nothing painful at all. So everything is just nice once you find it. Nonetheless, this is kind of a long story. And I will say this much about it. Where do I get this? I take a random partition. And so you say, okay, that's the first thing you would have thought of. It's the first thing I would have thought of. But proving that it works is another story. And what I would say about that is simply that the proof, I'll kind of mumble about what I mean. The proof is walk theoretic. It is not graph theoretic in the sense that when you're trying to, I have to show you that a random partition into a large number, an appropriately large number of blocks works. In analyzing this, I will never be looking at the graph. I will never be thinking about structure, graph structure, nothing of the sort. I want to think about how the walk is behaving. And for instance, one ingredient there would be some kind of finitary notion that's like recurrence versus transience, if this means anything to you. At any rate, that is kind of, that's what I can say about step 3. And I think I'm going to skip the riddle because time is a little short. So I'm going to move, that's the end of part of kind of the second part of my outline, and I'm supposed to move to, this page should not get your hopes up. We're still going. Okay, so I'm going to move to theorem A, unless there are questions. Okay, so I won't talk about theorem A in full. What I'll actually talk about is random walk on a regular graph. So not Markov chain, just random walk. And the graph will be regular. And so the condition in theorem A just becomes that whatever this common degree is, it's a big function of C. All right. This, by the way, is actually, this was the first result. This is where the whole thing started. So let me try to kind of say this. There are 3 pages here, and they kind of give you the proof, kind of. M is going to be the number of steps, so it's C times N. But the truth is, for a little while, I'm going to think about the whole walk. All right, and then we'll get to M soon. This will not play a real big role, but it's a standard character in this. It's the hitting time is just the first time you see the vertex V. Just 2 parameters. K is going, I don't care if it's C squared. K is a big function of C. All right, it's much, I just want it to be much bigger than C. And then P is going to be e to the minus K for reasons which will appear in a moment. The central notion is this RV. So we're doing this. We're watching the neighborhood of a vertex V and seeing how often it's visited. Okay, so this is a deregular graph. Every time you're in the neighborhood of V, you have a 1/d chance of moving to V. And I just keep track of those chances. And RV is the time when the number of chances to hit V reaches K times D. All right, I'm not paying attention to whether, I'm not yet paying attention to whether I actually did get to V or not. I just want to know how many chances I had. Okay, and then associated with this is QV, which is an event. It's the event that in all of those first KV chances to see V, you failed. All right, and QV will be the central player in everything that we do now. Okay, so this is, I had KD chances to CV. Now at each chance, I had a 1/d probability of success. So I really, on average, should have visited K times. And K is big. QV is the event that I never visited at all. Well, it should come as no surprise to many of you that if the expected number of visits was K, the probability that there weren't any is basically e to the minus K. And that's where P comes from. Okay, so the probability that a particular vertex does QV is e to the minus K, almost exactly. The expected number is then n times e to the minus K. Again, so I don't know how I did that. Sometimes I say e to the minus K. Sometimes I say P. The expected number of these vertices is NP. It should not be surprising that these events are negatively correlated, meaning if I give you a set of vertices called I, the probability they all do QV is at most P to the cardinality y. So if all of these guys failed to get hit, it doesn't make this guy more likely to get hit. It makes it, if any, sorry, it doesn't make this guy less likely to get hit, more likely. I can't. Okay, anyway, the stuff that I'm scribbling on now, this is all easy and kind of obvious. The next result is more interesting. So the expected number of vertices that do QV is NP, and it is concentrated. And this is a martingale concentration bound, all right? And it says, for example, I expect NP, the probability that I see fewer than 0.9 NP is exponentially small, which means I can ignore it. Right? Which means I don't have to worry about situations where this cardinality, the number of vertices that do QV, falls below 0.9 NP. I can just prove, I'm only interested in when it's bigger. One note here. This is for those of you who are somewhat martingaleized and know what I'm talking about. This bound does not depend, this bound is for the entire walk. It is not for the first CN steps. So this is a true statement, even if I consider the entire infinite walk. I will not tell you why, but that is a true fact, and for some of you, that should be an interesting fact. Let's see, I'm looking, okay, good. Here's a silly calculation. I'm looking for a set I of 0.9 NP vertices that all do QV. So here's a way to bound the probability that there is such a set. First, I choose the potential I, right? So out of n, I can choose 0.9 NP vertices. And then I have this bound number 2 in the middle of the page that says for any particular choice of I, the probability that they all do QV is at most P to the 0.9 NP. So maybe that's a union bound, maybe it's a good bound. It is not, it's a stupid bound, because what am I doing? I'm looking at n, this is a bound for a binomial random variable where I have n flips, each succeeds with probability P. The expected number of successes is NP, and I'm bounding the probability that the number of successes is bigger than 0.9 NP. This is not a good plan, right? But it orients us. It says what we should do, and it's on the third line here, we should try to limit the possibilities for I. Okay, so it shouldn't just be, it shouldn't just be any old set of 0.9 NP vertices I'm choosing here, right? Well, the thing is, we have something else, right? We're looking at vertices where, a shorthand for QV is this. That's another way of saying QV. The hitting time is bigger than, right? You don't visit in your first KV tries. But the other thing we know is that you do eventually visit V, right? We're assuming the walk covers. So in time m, which is, remember, m is c times n. In time c times n, you do hit. So it means you failed on your first KD tries, but you did succeed. So those first KD tries happened pretty soon. They happened before time m. And now if you think about it for a moment, I'm taking a walk of length c times n. The time I should spend in the neighborhood of V, the neighborhood of V is a set of size D. So the time I should spend in that neighborhood is C times D on average. But I'm telling you I spent K times D. So this is unusual, all right? And so now, I'm writing QV star for both of these things happening, for missing my first KD chances, but also getting those KD chances quite early in the process. And so now I have two things that are hard to do, and they should somehow conflict. I mean, that should give me some additional power, but you have to be careful, because now I'm going to skip this because we're about out of time. This was a Markov chain. The picture at the bottom was a Markov chain example to say you really can arrange that the vertices that you keep missing are precisely the vertices that you keep getting extra chances to hit. So the two ingredients in QB star actually can be very, very highly correlated, and it's not absolutely clear that you're really gaining very much by this thing at the top of the page. All right, but you are. This is the last slide. You see QV written up there. So do I have time to get through this slide?
Maybe 1 minute for quick wrap up.
1 minute. Probably I can. Let me not. I don't want to race through because it won't do anything. But let me say, so somewhere in this slide, and it's down around the bottom, you should see the role of big degree, because you haven't seen it yet. In fact, everything I've set up to this point is perfectly valid for general Markov chains. Well, not everything. KD doesn't make much sense, but basically what I'm saying is okay for Markov chains. Somewhere near the end, there was a punchline which said, this is how you use the fact that the degrees are big, all right? And maybe I can set it up just slightly. So let me talk about two lines here. Let me take Y to just be the multi-set of vertices that the walk visits, okay? And Z is going to be the set of vertices that do QV star. And the statement is that every vertex of Z has at least KD neighbors in Y, right? This was part of the condition. We visited its neighborhood. If B is in Z, we visited its neighborhood at least KD times, right? So it has at least KD neighbors among these C times N vertices, and that is unusual. And so if I go back up, this is kind of something that looks like asymptotic enumeration a little bit. If I go up to the red arrow that's now in the middle of the screen, this is limiting choices for I, right? I'm somehow saying, well, I has to be drawn from vertices that have a lot of neighbors in this set capital Y, and so somehow or other that gives me a way in this useless calculation, that gives me a way of doing something about this nasty binomial coefficient. And all right, so let me stop because it takes too long to say it properly. Oh, there's another slide. Forgot the last slide.
So before the question, let's thank Jeff.
You're welcome.
Let's have maybe 1 minute of quick questions.
Jeff, did I hear you say that the Benjamini's conjecture fails for multigraphs?
I'm sorry, say again?
did I hear you say that Benjamini's conjecture failed?
It's certainly wrong it's trivially wrong for multigraphs. So I give you the construction since it's so complicated. Take a path, and now start at one end and start, say, doubling the weights or the multiplicity.
Oh.
So that here's one edge, here are two edges.
Okay, enough said. Enough said. Yep.
Right. No, I know.
That's probably part of the reason why it's difficult to prove the conjecture.
Yeah, maybe. Well,
yeah, it's
I'm not
it's not Markov.
One thing I would for Pete and maybe a few others, if you promised to start with the stationary distribution, if X0 is stationary, I bet the conjecture is right. I don't think we know how to prove it, but I bet that's right.
Okay, thank you.
Any other quick questions? So yeah, let's thank Jeff again.